we will continue with the afternoon session with this new hands-on session. The second one, which will be dedicated to introduce the use of Kratos problem type within the GID framework for the study of monotonic behavior of a material using the isotropic damage model. For those of you who are familiar with the use of isotropic damage model and you prefer to use the isotropic plasticity model, it's also valid. I can help you on the process, but the explanation that I will give now is for the isotropic damage model, okay? So let's start. I've prepared a presentation and the format is basically the same as yesterday. I will give you we will start doing some review on the concepts that we've seen during the morning and also how this reflects in Kratos, okay? Because and not only from the use of the GID problem type, but from the perspective of the actual Kratos code, okay? Because some of the features that can be used for the isotropic damage model are not available directly on the problem type in GID. So we will need to edit the input files outside of the GID environment to be able to use certain features of the isotropic damage model implemented in Kratos. Okay, but we will see that. So before starting, well, we are here. At this point, we know each other, so nothing to mention. We will finish by 4 p.m., just like yesterday. And this is the structure. Okay, we will see it through the class. This is the QR to download not only this presentation, but also some of the files that we will be then using to run simulations. Okay, in here, I give you some minutes. You will find a PDF with the presentation and also a compressed file in RAR format containing one GID model, both geometry and output files obtained from a Kratos calculation corresponding to the first example that we will be seeing. So then you can just follow all the process that I will be commenting. And then some data which will be needed to then go through the second example. Okay, so basically this is the info. Hands-on session 2, it's not in here, it's in here. This is the information which is inside. This CSV file contains the data obtained or provided by an experimental campaign performed for a stainless steel, okay? Real experimental data. So this is just the info that we've received from the laboratory. Then this here is a geometry corresponding to a standardized monotonic tensile sample, okay? The one that has been used to do these tensile tests. And this here is the GID model that we will be using for the first example. And apart from that, you have also the PDF with the presentation. So let's see this presentation. Nonlinear constitutive laws in Kratos Multiphysics. So this is just an overview of what is what can be or what is accessible from the problem type. So this is the information that you see, when using the Kratos problem type and you are about to assign a certain material behavior in your model. Okay, this is the window that we've seen yesterday to assign material properties. And these here are actually the various constitutive laws that we have available in Kratos. These are just the ones for small strains, if I'm not wrong. Okay, We have here the ones corresponding to or to assign anisotropic properties, indeed it's orthotropic properties to a certain material. We have damage, various types of damage. We have plastic damage. We have here the high cycle fatigue. We have plasticity, both isotropic and kinematic, etc., etc., etc. We have viscoplasticity and so on. Okay. So this is just to give you an idea that even though in this course we are focusing just on Kratos seen from the problem type perspective, Kratos is much more than this. Okay. So if you at some point want to do a research using Kratos to develop your code, you will see that there are many, many other things that can be done using Kratos. Okay, this is just to give an overview. So basically, as I commented yesterday, I briefly mentioned it yesterday, and but because it is necessary to know or to give a closer look to these files today for today's exercises. These are the input files that GID is generating when we click on write input files no run. Okay, these are the input files that are then used by Kratos to run your simulation. So these 4 files here contain all the necessary information corresponding to your model, the one that you've created using GID or whatever other tool that you have to create the model that you want to study, and then are used by the Kratos code to perform certain type of operation and then produce an output file or various output files. Okay, which is the information that it's contained here inside. Indeed, this corresponds to one of the cases that we ran yesterday. Okay, the first file here, which is has extension MDPA, contains the geometrical information of the model. This is from a numerical point of view, nodes in your geometry. Then connectivities. This is grouping these nodes to convert this information into elements. Depending on the type of mesh that you are using, these elements will be triangles, quads, hexahedra, tetrahedra, whatever. Okay, so basically you are connecting nodes to generate other entities. It contains groups. It contains groups which basically identifies entities which are superior to nodes, for example, surfaces. If you then need to apply a certain condition to a surface, like a load, then inside this file you will find this sort of groups. Okay, to then identify these groups and assign the corresponding action. And then these submodel parts. The submodel parts are groups, other kind of groups of nodes and elements into which we will be applying certain conditions. For example, in here, if we want to apply a boundary condition, it will be necessary to identify the group of nodes on which we will be imposing the displacement. So these nodes here has displacement equal to 0. So we have created a submodel part in which we identify this group of nodes. And then if you go to another file, you will be referring to the name of this submodel part to then impose the corresponding boundary condition. So in here, basically, you have all the geometrical information and all the groups and of elements or of entities that are then used to create or to impose boundary conditions, imposing loads, applying material properties, etc., etc. Okay, everything, all this information is available on the MDPA. So if your model is 2 elements, this file here will be kind of short. But if you have a 1 million element model, then this file here will be much bigger, okay? Because the information will be longer in this case. In the main Kratos, this file here is the one that you are actually running, okay? This is whenever you run Kratos, Kratos is executed from Python. So if you run it as a developer, you will have your command window and you will write Python main Kratos py and will press exe if you are running it on Windows. Okay, for Linux, I guess that it works similarly, but not using maybe the same approach to run the simulation. But this is the file that it's running the case. Okay, so basically this file here is the one saying, okay, the information to be get for the simulation corresponds to these files here. So basically it contains the name of the files that needs to be called in a specific order. Okay, and tells to the code how the calculation is being performed. That's it. Then the project parameter and the structural material JSON are maybe the two files that contain the most interesting information for you. The project parameter is the file in which we are specifying the time discretization scheme that we will be following, which is the step, which is the starting time, the end time, etc., etc. We in here specify which is the solver that we will be using for running the simulation. The way in which the problem is being defined, this is basically which kind of problem are we running, if it's non-linear, if it's elastic, whatever. Everything is defined here. Which is the material input file that we will have. I'm not sure if it's shown here or maybe in another. No. Then in here, you can also find some inputs to describe the convergence criteria. If I'm not wrong, I have another slide to better see this, okay? And also some description of the outputs. And this imposed displacement and imposed load is basically the block that is shown here. So for example, for yesterday's exercise, in which we were fixing one of the ends of our sample, and in the other one, we were applying an external force, sorry, not an external force, we were applying the self-weight. You can see here how these two blocks contain that information. Okay, we have this process block in which we are introducing this constraint process list, in which we apply the boundary conditions in terms of displacements. So this one here is the one containing the information from the fixed end boundary condition. So from the beginning of the simulation, 0, 0, towards the end of the simulation time, n, we will be applying a constraint, a boundary condition, which has certain imposed value for the x, y, and z global variables with value 0, 0, and 0. So the displacement is not allowed. And this is applied to a model part name, which has been defined in the MDPA file, which is named or which can be identified as structure boundary condition fixed n. So if you open your MDPA file, you will find a block there, which this reference name or with this identifier, which contains the information of the nodes that are considered to or on which we will be imposing this boundary condition. Okay. And then the same for loads. Well, the block looks more or less the same. In this case here, what we're applying is a modulus, and then orientating that modulus. That's the idea. And then we have this last file, the structural material JSON, in which basically we are describing the various constitutive laws and material properties that then will be applied to certain elements in our geometry, in our model. Okay. Yesterday, what we built yesterday was an homogeneous beam, and so we only define one part to be applied to the entire geometry. And this is basically what you can see here. If you remember, in that part block, so it was part, solid, and then you had there all the options. We defined there the type of constitutive law that we were using, the type of element. The element is not defined here, is in the MDPA. But in here, you can see this line here is identifying which is the constitutive law. We were using linear elastic plane stress 2D law. This is the name that is used inside Kratos code to identify this constitutive law. Okay. For the damage, it will be isotropic damage or small strain damage to the law, plane stress to the law, and so for other laws. I will give you the references. And then here we have inside the variables that described or that are needed to run the simulation. In this case, these are just elastic properties. Now, how this then is particularized for the isotropic damage. This is a structural JSON example, a structural material JSON example for an isotropic damage model, for an isotropic damage simulation. Okay, it looks more or less the same as this case here, as this structural material JSON, but there are some new variables that are identified here. Okay, if we let's open GID. If in here if in my GID project I open the Kratos problem type and I create a basic model, let's do whatever, just to be able to see what is the specific information that it's required to be introduced. So this is my geometry, okay? And now I want to see which are the variables that are introduced, are input from the GID problem type windows. So in here, I leave it as a small strain case. And now instead of selecting the linear elastic case, I look for the small strain isotropic damage. And for example, let's select the plane stress case. Now, all the option section has been updated. Okay, which are the information that will be introduced or that it's asked to be input here as data? The density, the Young modulus, the Poisson, and the thickness, which are basically the same data that we introduced for the elastic case. But apart from this data here, we are asked to introduce the yield stress, which then will appear here. The fracture energy, this is joules over meter square, which is the energy required to open a crack in the material. And then the softening type. This softening type is the variable that defines the shape of the threshold function. Okay, 0, the number 0 here is linear elastic softening. Sorry, linear softening. Number 1 is exponential softening for damage. Number 2 is a law which has some hardening followed by softening. Okay, but it's a continuous function. And number 3 is the by points function. Okay, today the simulations that we will be running, I will ask you to use number 1 and number 3. Okay, so exponential softening and by points curve. The point is, if you want to use the by points curve, and you then write here number 3, nothing has changed. But in order to use this number 3 threshold function, you need to introduce new input information. Okay, this new input information cannot be added from the problem type, and this kind of information needs to be directly added from the material JSON file. Okay, that's why I'm presenting this class from this perspective. So in this case, basically what I'm running here is a simulation in which I will be applying these material properties to my geometry. Okay, and these material properties corresponds to isotropic damage model, plane stress with certain elastic properties, then a yield strength of 500 megapascals. 5 megapascals, fracture energy of 500, and softening type 1. This is just randomly written material properties. Okay, this does not correspond to any real material. Here, which are the options? This is the way in which the constitutive law name is being defined. Okay, in order to use the isotropic damage model, this is the structure. You write small strain isotropic damage, followed by plane strain, plane stress, or 3D, and then the corresponding yield criteria, or in this case, because it's direct, there is no stress integration process. This is the way in which the equivalent stress, this uniaxial measure of the stress, will be computed. So if you write von Mises, then this S sigma that I introduced you on the first talk in the morning will be computed according to the von Mises criteria, which is a square root of the 3J2, right? For the modified Moore-Coulomb, the same for Tresca, Ducker-Prager, Rankine, and Simoneau. And I think that there are other, but I have not included them. Okay. Then for the material properties, this is a description of what's the meaning of these basic material properties. But the best thing that we can do is just building a case and modify some of these properties and see which is the effect that it has on the response of the material, just to get familiar with the meaning of these material properties. Because in this case, all these material properties have some real meaning, okay? So these are not just calibration parameters, these are parameters that have some physical sense. Then for the type 3, this by points curve, the extra information that needs to be introduced in the material JSON problem type in the structural material JSON that I have not included in the previous slide are these two vectors. Okay, so if you want to use the number 3 hardening law, apart from the other information, the other variables, you need also to include these two variables here. You can see the example in the example that I shared with you, this GID case. Inside, I'm using the by points curve. So inside you can see which is the kind of information that is included here. But the structure is as follows. The first point corresponds to must be the yield stress and the yield strain. Okay. If you do not include this initial point as part of the vector, then you will get an error from the simulation. And then at some point, you should also include something close to the ultimate strength of the material. Okay. Once you finish the list of points for your by points curve, the curve will continue showing exponential softening behavior. But this is done in an automatic manner. And this is the analysis of a project parameter JSON when using the isotropic damage model. Okay, what's here? And this is a pretty in-depth analysis of the information, the data that you will find inside this project parameter JSON. You can identify the starting and the end time for the simulation, which are doubles. Okay, the time step strategy that you will be following during your simulation, and this can be defined in two ways. You can just write here, instead of time step table, you write time step. This is wrong. This should be time step table. If instead of time step table, you write time step, then here, what you should be providing is just a double. Okay, so 1, 2, 3, 0.1, 0.001. During all your simulation, from the initial time from the starting time towards the end time, each increment in time, so from one step to the next one, you will be incrementing 0.01 seconds, okay, based on your time step. And this here, this other way, this alternative, is just to create let's say more specific strategy to have various types of time steps during the simulation. Imagine that you are just applying one specific load, but as you get as the nonlinearities evolve in your simulation, it will be more difficult to converge to a solution. So it is a good idea to reduce the time step as the nonlinearities accumulate. Okay, So if you want to do that, you have two options. You create two different loads with the same modulus, but different rate of application, or you modify the time step that you are using for your simulation. This is an alternative. This echo level, this is something that I already mentioned yesterday, which is basically, if you set it to 1, it is set to 0 by default. But if you change it to, if you switch to 1, then you will get information from the simulation. And as we will be running nonlinear simulations, knowing the amount of iterations that it takes to the model to converge, it's quite useful information. Here we are calling the structural material JSON that contains the material information for our model. This here, this block contains the information necessary to set the convergence criteria during our simulation, amount of iteration, and so, etc., etc. And this block here is the one containing the information about the boundary conditions and the loads that can be applied. My recommendation is to avoid using loads while we are using or while we are running a nonlinear simulation, because usually while you are imposing a load, what you want to be imposing is a load which increases with time, okay? And if you reach the softening phase of your material, then you will not get convergence. While if you work with displacements, impose displacement in your model, then the convergence can be reached, even during the softening phase, okay? So usually I will not recommend you to use forces while running nonlinear simulations, unless you use other techniques like arc length algorithm and so that are also available in Kratos. And this list other processes is a block that can be used to printing certain information. Yesterday, some of you asked me if there is a way to obtain as an output of the simulation the summation of all the reactions at a certain part of my geometry. Yes, it can be done. You will be getting a TXT as an output from the simulation, but you need to tell Kratos which are these points from which you want to know this information. And this is being introduced in this block here, in this list other processes. Yes?
Can you also put an image pattern?
Yes, if I'm not wrong, yes. Indeed, you identify which is the type of extension, but I'm not sure if it changed something. I should double check that. I know that you specify that you want a TXT. I usually want a TXT because then I use this to load it into Python or something like that. But I'm not sure if you can get an H file.
There's also some libraries that make H template processing.
Mm-hmm. Yeah, I'm not sure. Alejandro was the one implementing this printing file process, which is a Python process in Kratos, and we can have a look if you want later.
For the time step table, do we have to ensure that the time step that we define matches the next time
basically
that we define?
In here, what you're saying is from 0 to this. So if you just write 0, 0, 0, 1, from this point till this point here, to the end of the simulation, the time step will be 0, 0, 1. Okay, and from that point on, basically what I'm setting is ranges for which the time step will be that specific value.
My question is, if I define, for example, not 0.01, but 0.03.
And then in the other one,
if it doesn't, it most likely would not match 1.099. It doesn't matter.
No, it doesn't matter, because basically how it works is it looks for which is the time step to be applied. Okay, now I know the time step. I perform my simulation, whatever, or I update the strains, then I compute and do the calculation of the stresses. Now everything is solved, and I ask to Kratos, okay, which is the new time step to be applied? And it will ask you, which is the current time? So it will go here in the table and it says, okay, my time is 1.0987, which is still below. Yeah, so it will check that.
There's no way to change it,
Yes, there are some ways. You mean restarting the case from specific point, right? Yes, the restart is also implemented in Kratos, but if I'm not wrong, by default you are using or you are creating post-bin files as post-process, and I think that you should move to ASCII post-process file, because then you should be printing a specific kind of information to then be able to relaunch the model from that specific point. But I'm not that familiar with the restarting. But it's something that is available in Kratos. If you have a look at the constitutive laws in the H files, at the bottom of the H files there is something named a block named serialize or something like this, containing the various member variables of each of the constitutive laws, and this kind of information is the one that then is used for the restarting purposes. Okay, so yeah, it is available, but I'm not sure which is the process, exact process to activate it, because you need to store quite a lot of information from the previous steps. Okay, this is something that I've already mentioned about how to create a React. No, sorry. This here is the blocks that you can use to generate these files that I was mentioning. If you see here, when you specify the name of the file, we are adding the extension, txt. So I'm not sure if you change here the extension, if it will write it in the corresponding format that you want. Okay, I'm not sure about that. And this is also to mention that apart from information at the node level, you can also obtain information at element level. So most of the variables like damage, the stress tensors or the stress tensors, also the internal variables of the model, the plastic dissipation and so, are not computed at node level. These are computed at integration point level, which belong to the element. Okay, so the information that should be retrieved from the calculation is not nodal information, but elemental information. And so the structure is a little bit different, but it can also be obtained. And then this last block is the one regarding the post-process. Okay, in here, you're specifying which is the type of post-process that you want to obtain. As I was mentioning, this is by default GID post-binary. If you try to open that file, it's just random numbers, or it seems like a corrupt file. But there is a way to switch from this to ASCII formatting, and then this is the one that can be read to the restart for restart purposes. And then there are some other options in here. The way or the type of information in which way is being stored. If you want to specify, oh, okay, I only want to store results after 10 steps, or after each 1 second. Imagine that instead of using an implicit scheme, which is the one that we are doing here, you use an explicit scheme, and then your advancing time, your time step is really, really small. You do not want information for intermediate steps, because this consumes quite a lot of memory. So what you can do is just define here that I want to store the information after 1 second of time, real time of the simulation. And so you will be storing just few results. Okay. And in here, the information that we were specifying here in Kratos, in this part here, about which kind of nodal result and elemental result we want to obtain as post-process, in here is defined in these two vectors. Okay, what is important here? To know the exact name of the variable that is used to implement that variable in Kratos. Okay, in here I'm just mentioning some of the most common ones: the damage, the uniaxial stress, the Cauchy stress, etc., etc. So in here you can write the name, and you will be obtaining as post-process this information. Yes. in Kratos, if you want a value on a node, you should obtain it as a post-process, as a TXT, or to visualize it in GID. What do you want? In a node, then you should add this kind of block.
So we have to write it on, you can do this in the Git.
You can do it in the Git, but then you need to know exactly which is the node for which you want it. I mean, you can do it in Git, but you need to open the post and so. But if you a priori know which is the node, the ID of that node, it is better to do it here, because then you will get this sort of post-process file output file. This one here. This is the case that I send you. Okay. Okay. For example, this one here. No, this is damaged. Sorry. Let me see if I have a displacement here. You will be getting this displacement corresponding to a node, or maybe this is the summation of a group of nodes. Okay, so it's just copying and inputting in Python or in Excel or whatever, and just treating the information. And you do not need to open the entire model, select the point, etc., etc. So this is a fastest way to proceed. Saying this because usually when you are preparing a simulation, the first time that you run the model will not work. So instead of waiting until this finishes, going into the model, selecting the point, going to Excel, seeing the results, this is just generating a file which is being updated from step to step, copying the data and going to Excel, and that's it. So you can easily control the evolution of that parameter. I was here, right? Yes. Then this is, I would say, pretty fast overview of the features or the main an overview of how a damage model look like when using Kratos. Okay. Now it's time to run a simulation, and I prepared 2 examples. Let me just check something because I'm okay. And the 2 examples are the first one, this one, which is a dummy case. Okay, nothing in here will look like reality. So the material properties that we will be using, they may look like they are real, but they are not, because this really depends. I mean, the way in which we will be imposing the boundary conditions result in a kind of situation that it's not realistic, or will not allow us to really retrieve something physical sounding, but it's really useful to really understand how the model works. Okay, so basically this is something that we usually do whenever we want to check if the implementation is doing exactly what we want it to do, which is creating a geometry that behaves exactly as an integration point. This is all the stress state and all the strain state for this element here will be the same during all the simulation. Okay, how do we achieve that? By means of the boundary conditions. Basically, what we are doing here is constraining the x displacement in this direction, in the horizontal direction. So this point here cannot move in the horizontal direction, and there is a point here which can neither move in the y direction. In this way, when we apply this horizontal displacement, this element here will start deforming. It will start deforming, and so the shape will be like this, okay, with some extension. But the stresses will be uniform everywhere. Why? Because we are allowing this point here to deform. Okay, the Poisson effect is not introducing stresses in our material, in our structure. So the stresses are uniform everywhere. So all the integration points behave equally. And this is basically like studying the behavior of one integration point. And this allows us to properly study or see which are the response or the implementation that we've done for the specific constitutive law. So this is kind of useful. Okay, and this is the model that I prepared for the first case. And this is the one that I've sent you. Okay, we will open it now. Okay, the version that I've sent you of the model is not this one, is this one here. So if you open now the model, which is basically this one here, I've opened the GID, I've load the model. Okay, I open the folder, the GID folder, and after doing that, I move to the post-process. If you do not want to do this or to work in this way, you come to the folder. Once you've uncompressed it, you go to the Git output folder, and you just open this into GID. Okay, and basically you will be obtaining this post-process file. Now let's see which are these results that I was showing. If you click on this button here, you will be able to create charts in the GID environment. Okay, what I want to check, I'm just imposing a monotonic, an imposed displacement on this right-hand side of the element, which is increasing with time. Okay, so let's see how the uniaxial stress, which is the uniaxial measure of stress based on the yield function, on the yield surface that you are using, in our case is von Mises, how this evolves with time. So I click here, and then I will be selecting a node in my geometry. Remember, all the integration points have exactly the same value. Okay, so even though I now select a point, a node, the value will be exactly the same as an integration point, because even though it has been interpolated by GID, the value will be the same. So in order to select a node with the GID, the way to do that is to selecting the node. But if you have this cross mouse, let's say, figure, look, you have, by default, while you do that, it will appear this shape on your mouse. Okay, this one here do not allow you to select a point, a node. It will allow you to select a random coordinate in the space, but not a one coinciding with a node. Let's say, the mouse mode that allow you selecting a node is that one which has this shape in GID, this one here. To switch from one to the other one, you must do Control plus A. If you do that, you will be switching from one to the other. Let's see. Control A. You see? This is the square with the point in the middle. And if I press Control A, I switch to the cross. Okay? With Control A, now I can select the node. You see? Enter one point. If I click any other place in the screen, nothing is being selected, because this way to select points in the space, it's just expecting for nodes. So now that I've selected one point, I click Escape, and then this chart is being generated. This is the evolution of the uniaxial stress measure in my model due on a long time, okay, along the simulation. So basically what I've done here is I've generated the model, I've assigned just one element, one quadrilateral element to this, to mesh this geometry here, and I've defined the material properties corresponding to damage model. In here, what we have is damage. Let me just show you that we have damage. So instead of plotting the uniaxial stress, let's plot the evolution of damage with time. This is the evolution of damage. So we are using an isotropic damage model, 2D plane stress, and we are using the by points threshold function. So this means, because if you've seen, we have this initial hardening phase followed by the softening, exponential softening. This means that if I move now to the structural material JSON, what we should see inside is isotropic damage, small strain isotropic damage, plane stress, von Mises. Let's have a look. Project structural material JSON, small strain isotropic damage, plane stress, von Mises. Okay? This is the case that we are running. And now, I told you, we are using the threshold function number 3. Threshold function number 3. Okay? And these points here are the ones describing the hardening process. So, just because this is a one-element case in which all the stresses at any time of the simulation are equal in the entire geometry, the information that is given here should be directly reflected in the model. For example, yield stress is 400 megapascals. So if we go now to our model and see when the change from the elastic response to the inelastic response take place, we should see that the uniaxial stress is exactly 400 megapascals. We come here, we open the chart, we move back to the stress here, and here, this value, even though it's not that perfectly shown, it's 400. Okay, I have also the value in an Excel file. Oh no, not this here. You can see it here, okay? This is the point, exactly 400 megapascals. This is only possible because the stress state at all the geometry is 400. Of course, if we are now moving to a more general model corresponding to a component in a vehicle, to even a tensile test sample, this initiation of the nonlinearities observed experimentally at the sample level doesn't need to match with the initiation of the nonlinearities at the material point. Okay, and this is something that Lucia has initially explained this morning. This is crucial, okay, because now for the second exercise, what I will be giving you is only experimental information. And based on the experimental information, you will need to calibrate your model. And you need to decide which is the information that corresponds or that better describes or that allows you to capture the response observed experimentally. Because numerical technology is a mathematical abstraction to obtain the real response observed in a material. The reality is the experiment, okay? There are many things to be considered there for the experiment, but the reality is the real behavior of the material, the experiment. So you can obtain whatever you want here in the numerical model, but at the end, you need to capture the reality of the material, the experimental part. Okay, these are just mathematical abstractions to being able to capture that behavior. Okay, and the important thing now is to really understand how the two walls connect. What is the meaning of stresses in a tensile test for an experimental engineer, and how do you use these stresses in your model? Because they are not giving you stresses, they are giving you engineering stresses. So what's the difference then? And they are not giving you strains, they are giving you engineering strains. And what's the difference? How this connects? And they will give you the yield, and they will say yield sub 0.2, which corresponds to the strength of the material or the stress corresponding to a total accumulation of plastic strains of 0.2 or a strain of 0.2. How this connects with the yield variable that you're inputting in your model. Okay, these are the questions, because otherwise you are just creating mathematical models. So now it's time for you to work with this second case. You can start wherever you want. what I'm giving you, this CSV file, are the points corresponding to one of these two curves. The two curves are more or less the same, so you can just work with one data set. I'm giving you here the geometry. I gave you one which IGS file that can be imported into JIT to then create the mesh. Okay, so I'm already giving you the geometry. If you prefer to create it on your own, it's also fine. And I'm giving you all the information that we've received from the experimental guys. They gave us the density of the material, a Young modulus, a Poisson, a yield, and this UTS stands for ultimate tensile strength. Okay, this is the maximum strength of the material along its life. And I'm telling you, these are engineering stresses, these are engineering strains, and these red points, which are the strain gauges, are the points in which the experimental, the guys in the laboratory introduce the gauges to measure the deformation of the sample during the tensile test. Okay? And now I'm telling you, this is a stainless steel, and tomorrow I want to simulate a component in my car made of the same material, and I want to know the performance. So the first thing that I need to do is calibrating the numerical model. Okay? You can work on that now.
Is there a geometry file 2D or 3D file?
Sorry, what?
El archivo de geometría.
Os lo he dado, es un IGS.
¿Es 2D o 3D?
Es 2D. Os lo he puesto en 2D. Podéis correrlo en 2D o en 3D. And what I'm giving you, this IGS file, is just a geometry file that I've created using AutoCAD. And in that, I created the divisions, the sufficient divisions, in order to being able to detect or to position these points here. I'm giving you just 1/4 of the sample. It's up to you if you want to run 1/4, 1/2, the full geometry. Is your decision. Okay? You need to decide if the symmetry conditions can be applied to this geometry or not. This is just a sample. I mean, this is the easiest, the easiest geometry which you should be starting. Okay, everything starts from this sort of samples. If anyone at home has any question, just let me know. Okay, I will be here. I think that the only thing that you can do is raising your hand or writing in the chat. Now let me switch the mic because it will be easier for those at home to listen us. And I open it here. Yes. This is the element, the one element. This is the mesh. This is not the job. This is the mesh. No. If you do that, you will lose all the information. It's not because the calculate. So if you click here in calculate, this operation will do both. Regenerating the input files, which cannot be regenerated because then you will lose all the information that has been input outside of this environment. So you cannot do that. You cannot rewrite the input files, and then running the simulation. You can see the piece here. MDBA and JSON written okay. So the files that I gave you have been modified. This is basically what I'm telling you. So what you should be doing is downloading once more and compressing once more the info that I sent you to obtain the files that I sent you. And instead of clicking on calculate, you should go to Kratos and run without run. Or basically, if you go here, as I've already, I've sent you not only the geometry and the mesh, but also the results of the calculation. Okay, so you should regenerate the. You should do that. If it's, I think that the all it's in Kratos. I'm not 100% sure, but I would say so. If it's already in Kratos, you can use it. You should download the code, or at least go into the GitHub. Maybe if you are not 100% sure, maybe you can in the GitHub write a question there. So someone, for example, in this case, is for the structural mechanics application. Someone from the structural mechanics application will answer you. And if not, you should code that. Here's the whole thing about open source. Anyone can do it. Well, if you want to import and IGS. The first one. Then you click on the IGS file of the segment and it will open. If I'm not wrong, the issue with the file that I sent you is that I used AutoCAD. And so some of the lines, even though it seems that they are intersect and so, they are not. So in order to create the surface, you will see that you will find some problems. So let me just do it. Let me just do it and let me show you how to solve that. So what you should be doing now is going into File, Import, IGS, and then looking for, let's look for that file. So let's open the folder, and this is the IGS. And this is that file that I sent you. It looks like it's points, geometry, whatever. Okay, but if I try to create these surfaces, so the surface and do it in an automatic one, or you will see that the surfaces that have been created do not really respect these divisions. And this is because the geometry that I provide you, which I made with AutoCAD, is not really considering this point here as an intersection. So before doing the surfaces, what you should be doing is ensuring that the intersections are properly done. How do we do that? You go to Geometry, Edit, Intersections, and then you select lines. Let's do that. Now we select all the lines in my geometry, and it will tell you 16 lines divided and 0 new points. Okay, this is because the points were already there, but there was no physical intersection between some of the lines. Okay, and now it is better. What I recommend you anytime that you receive a geometry, which it's not made like you, is go once more into the geometry edit and click on collapse. Because if there is some repeated line, for example, in AutoCAD, maybe I repeated some of the lines. This will detect that there are some overlapped lines that shouldn't be there, and they will be collapsed and reduced to just click here, collapse model, and it will tell you, in this case, collapse model created 0 points, 0 line, 0 surface, 0 points. So nothing has been changed. So this is good. The model was already done. And now, if I do once more this creation of the surfaces using exactly the same approach, for here, I'm obtaining a correct division or creation of surfaces. Okay. So you need to import it into CI. You want to try to import and just like here. This material that we are calibrating now for monotonic purposes is the one that we will be calibrating tomorrow for isotropic purposes. Okay.
Yo no puedo subir un desplazamiento tendría que, digamos, la simetría de acá para abajo, creo que sí, pero de acá para acá no. O sea, creo que lo que quiero simular es empotramiento y fuerza en este lado. Y acá si pongo empotramiento no pegues.
Yo te digo lo que pasa. Toda la parte final de la probeta, en realidad son zonas que van a en la fila de Eso está hecho así específicamente para que este tipo de cosas, que son cuadradas. La no linealidad no ocurre en la zona de ciclo, se produzca en la zona conceptual. Vale. Entonces, en realidad, el tipo de condición de contorno que le pongas a la zona de gris te va a dar igual. No va a cambiar mucho, porque el estado de tensiones se va a redistribuir lo suficientemente rápido como para que la zona del centro le importe un pimiento lo que le pase en la zona.
Si lo pongo a ver,
Entonces, si tú aquí le pones condición de desplazamiento nulo, lo que estás haciendo es desplazar tu cámara. O sea, ellos, evidentemente, fijan un lado y el otro exterior. Entonces se mueven las dos. Lo que tú estás haciendo es mover tu cámara de visión por el centro. No hay ningún problema con eso. Lo único que tienes que saber es que un desplazamiento aquí de tanto, en realidad quiere decir que aquí es el borde. Pero poderse se puede hacer. Yo estos casos que los hago con 3D, los hago con un cuarto de probeta y la mitad de espesor. Algo que decía Lucy, with respect to something that Lucia has mentioned this morning, about the connection, the relation between material and surface. These are standard examples. Okay? There is a reason because to this specific geometry, and the reason for this specific geometry is that non-linearities, the failure process will take place starting from here, but rapidly advancing and progressing towards the center. Okay, this is the way in which these geometries are being built. And if you have a look at the standards, most of these tensile samples have this shape here, this dot-bound shape. Okay. While for the high cycle fatigue test cases, there are other kinds of geometries. They also have dot-bound samples, but the central area, this reduced width area, is not that long. But there are also other kinds which are the hourglass kind of samples. And the point is that in here, in these samples, there is also some geometrical effect. But because we continue imposing the displacement or the force, the stresses and the nonlinearities are more or less homogeneously distributed in the entire width of the sample, and this geometrical effect is not that important. But for fatigue geometries, for fatigue samples, just because we are staying always, at least for the first 100,000 of cycles, in elastic domain, the influence of the geometry is crucial to define the evolution of the nonlinear process of this, which was the name that we were using, hidden nonlinearities evolution or invisible nonlinearities evolution. Okay, but here we have also the geometrical effects, but they are not that important. And this is the reason why the kind of input that you will be introducing in your model to calibrate your model, this hardening part of your curve, the values that you will be inputting there will be pretty much the same as the values that the experimental guys obtained during the experiment. Because what they are measuring, what they are giving you, these engineering stresses, what are these engineering stresses? These are forces, they impose force by the machine over the initial section. Okay, this is our engineering stresses. In our model, what we are inputting is the behavior of a point. Okay, but this point here will not behave like this point here. Okay, that's true. But because of the type of test that we are doing is a tensile test, and the stress distribution results in pretty homogeneous stress state in all this section here, using a calibration which more or less matches the experimental data will result in a pretty good calibration of the model. Okay, but this is not happening for fatigue. This is the difficult part in fatigue. That when you need to use experimental information, you need first to treat that experimental information. Right. But this is the problem that I was commenting before. This is because you have some nodes in here that are not really generating any intersection. So you should erase first the surfaces, even here, select surfaces, where is the now let's make the intersection. Go to geometry, edit, intersection, and then line. And you select all the lines. Let's see what happens. 4 lines divided and 4 lines dividing. So there were some points in here that even though they have a point, they are not really divisions. So now GAD has detected that, and for each node, it has introduced an intersection. So now this is a line, this is a new line, new line, new line, new line. Now, what we need, once you've done this, what we will do is because it has some. No, because it was not detecting. So your line instead, even though what you're seeing here is a line from here to here, maybe the line is not from here to here. The line is from here to here. Okay. So now you should be doing, before meshing, go to geometry, collapse, collapse, model, everything is fine. So even the surfaces now, and then go forward. Now you can see that the surfaces are fine. Now you go to mesh. Yeah, I know why the choice is good. This is because what you see here, the layers, I guess that some of them, you are creating the geometry of them, some of the layers, but the information is divided in some of them. So what you should be doing is sending the info, send to I will be sending all the information to this. Not let me erase the other one. It is the only thing they are not to have it here in the world. You should get it. You have grad, you open grad. One. I mean, Kratos seems to be open because the Kratos name was in here. And once Kratos is open, it will not allow you to create a mesh until you have defined you have not applied the properties. So let's do it this way. Let's assign the properties. Yeah. Let me just add some random properties to see that everything goes well. Let me select the right tips. Select you can do it in a automatic manner, or you can create them because the intersection is not so basically what I gave you, it's like if you click here, if I click in one of these, you should be able to. Because this node here, or there are multiple nodes in here. So the node is not connected, which belongs to this line. There is in here, if everything is fine, we should only have one. Two elements. So there are two nodes here. These are two nodes. We should be doing this for us. Let's try to do it with the short section. Minus the points. So there were duplicated ones. Every point was duplicated. Now you should be able to I'm not sure. Let's double check that it has not duplicated. These ones here should be just.
Un punto relacionar el y la parte del fracture energy es tamaño. Esto no.
Tenemos que coger los datos y hacer la integración.
Yo lo que haría es poner un número muy alto y a partir de ahí lo consigo que funciona la parte por puntos. La parte por puntos, a diferencia del resto de las curvas, no es dependiente de la energía. O sea, el modelo lo que hace es comprobar si la energía de fractura es suficiente para abordar esa zona y con la energía remanente hace la parte. Eso es como va. Por eso, cuando se utiliza en plasticidad, hay que asegurarse que solo se utiliza hasta la parte del pico, porque después aparecen temas de localización y demás, y hay que dejar que la energía de fractura evolucione momentáneamente. Si no, estaría asignando valores de energía diferentes.
Entonces, ¿cómo asignamos el dato?
Entonces, lo que debéis hacer es ir a, if you want to calibrate the threshold function, what I would suggest you is you should open the CSV file, create a chart, and then propose a list of points that match the behavior in terms of strain and stresses for this nonlinear regime. For example, after having done many calibrations, I worked in a Python script together with my mate ChatGPT. I came out with this Python file here. Okay, let me run it. I'm calling the same file that you have there. Okay. I'm running it here. Let me just open the other computer because I think that I have not the libraries.
La fractura aproximada.
So basically, I have this file here. I switch the whole thing. And I'm obtaining this sort of parameterization of the curve. So instead of using all the amount of data that experimental guys have given me, I have now a new list of strains and stresses for all this curve, which is more synthetic.
And the criterion, what it is depending on
The criteria that I follow to set the points. The algorithm is specified here. Where is the name? Using the Runner-Douglas-Tucker algorithm. It's an algorithm that checks for changes in slope and so with the respective in X and Y directions. And based on a certain criteria, I'm telling it, I want a maximum of 20 points. And so once it detects that a significant change has taken place, it selects a new point to be introduced. But I can switch the amount of points and obtain more points or less points. But it is going automatic. So there are ways to do that. It's to, like, for example, Lucia has mentioned, instead of just inputting the random numbers, we develop some algorithms that do this calibration process in an automatic algorithms that we have.
Okay. Then you should, okay, from this data, you select those points and you. So the factor energy, as you said, you just have to put a really high one.
A really high one, and then for sure this value will not be true.
And then you
But
bring
then
it down.
you should reduce it. But let me show you something. Let's go back to the presentation, please. What you have in here is the stress strain result, tensor result on that side. Look at the engineering strain percentages.
When you finish cooling, you calculate the energy by
Yeah, but what are we using? We are using a small strain isotropic damage. This is not a small strain. So this process of softening will take place for finite strains, for a region in which your model is not prepared to retrieve good results. So you can put whatever value you want, but I will not be interested in results on this region because this is out of the scope of the model. So as far as you are able to capture this part here, it's perfect. In my case, I arrived to 4% if I'm not wrong. This was my calibration that I obtained for this material.
we just agree that you told us the 0.3 max
Yeah,
value.
I don't mention that. Indeed, then what happens for high cycle fatigue regime? In the high cycle fatigue, we will stay here, below the yield. And what happens with the low cycle fatigue? In the low cycle fatigue, we stay usually below the ultimate strength, and indeed below this region here. Okay, so we are really on the 1 to 2% maximum. Okay, which is 0.01. Right? So you can stay there. Yeah. So the calibration that should be that you should be obtaining now is for this region here, because otherwise, if even though you are able to obtain good calibration for this region here, the results that you're obtaining are not really realistic because you are using a small strain model to reach this finite strain region. Okay.
If you put that really, like, what I don't understand right now is assigning a really high factor energy, what results would they?
It will allow you to run the simulation. If you do not, if you run 500 joules per meter square, basically it will tell you this factor energy that you are providing me is not enough to arrive to this point here, to arrive to the second region in which I will be doing this exponential softening. This is the reason. So you can write wherever value you will be describing points for this curve up to this point here, in which you will have the ultimate strength, but this point here is already above the beyond the small strain regime.
No,
Esto usamos el teléfono.
Si no, no vas a ser capaz de calcular
debajo de
vas a tener algo de crecimiento, pero vas a tener que poner energías altísimas. No vas a poder llegar a
500.
cosas tan
380. ¿no? Pues ya está. Esos 33. Selecto. Ahora tengo que meter las conditions.
just one comment for tomorrow's session. Remember that tomorrow we will be having the summer school not in this building, but on B0. Okay, B0 floor 1 in the 3D room. Okay. If you have never been there, you just go to the B0 building, which is everything right there. Okay, you enter, go to the first floor, and once you enter, the first room that is on the right hand side is the 3D room. Okay. It's a central room with glass walls, so you will see there what's the wall.
Pero depende de la simetría, eso obviamente es cero. Pero en este stage, no sé si lo hago, es ya strain constante o fuerza constante. Hay que describir un rate o una fuerza. Bueno, hizo, no sé si la hizo esta, es solo el tamaño. Creo que es un prescribe. Ha dicho que las universidades mejor prescribe y creo que no es claro, antes de la independencia, pero si la independencia que tendríamos que hacer, es una creencia independiente, le prescribimos también una boundary condition analog que se hace al área. No podemos prescribir, no. Sí. Do you have any concept of you have no path? Okay. Should we start the calculation, but it has nothing to do with those. Let's check. Yeah. I mean, it's the first time. Yeah, come on. Let's see what we can. You have created a material which contains, okay, there is a problem with this. Let's switch to this. Because if you write here the 3, then you need to introduce also the 2 vectors. And if you are not introducing the vector, basically the simulation cannot run because it will be looking for some information that is not present. For sure, it's easy to do something that can. So yeah, the thickness. This may be quite huge because what I'm telling you is millimeters. boundary conditions. You have imposed 3 boundary conditions, which are X or Y. This is for this here. But it's also imposed here. This is not correct. No. This is 5 and 3. So the 2 is not used, which go out. The 4 is not used, which should go out, because otherwise something will be wrong. 5 is the value imposed of 2 meters. Well, this is huge. Millimeters, yes. But this may be just impose this at once. So maybe it's trying to enter into the elastic regime and it's to like, let me just switch this to 0.8. Doesn't matter. What I want is to ensure that everything is under elastic mode, because I just want to run the simulation, make sure that that's, I don't want to do anything else. Then the definition of the load I can read directly from the JSON. So let's take this here and let's assign it to the correct. So this is not set. Then let's apply it to this only this. So this initial load, which was here, so we have the 3 boundary conditions and then the material property. Now let's remesh. And save, and we have now. You can do it from the mesh, but you need to impose other conditions in the calendar. So now let's write the calculation files, and now let's try to run this calculation. Let's see if everything's up. This seems like it is. Let's see the displacement. One. This is the under condition. Which is composed of the which is this set. That's this was 5. So is this mesh?
Yo le he metido a uno primero para ver que funciona todo. Y una vez con esto, pues ya estudiamos los 3 y me quedan 2 puntos y 6.
So we should close the session
Okay, and we meet tomorrow morning at 9 a.m. Okay? Bye to those at home. See you tomorrow.